Okay, this is a banana. And I'm kind of hungry. And so what I'm going to do is I'm going to peel this banana. Now, I peel the banana from this end, you guys. Okay. A lot of people, they peel the banana from this end. It's totally wrong. Okay. You peel it from this end because you know that little black little thing right here? I always find it really annoying. And I don't want to finish my banana by having to deal with that. So if you peel from this side, it comes off automatically. And then when you get to the bottom of the banana right here, it's all perfect. You don't have to worry about it.
Wouldn't you want to start out with it because it's perfect, like on the top?
I like to end with perfection.
No, but on the end.
Okay. All right. So anyway, let's move on. We can't let this divide us. Now, this banana has what we call energy in it. Energy. Energy is the capacity, the measurable capacity to make changes to your environment. It's a very abstract concept. Energy is kind of weird. It's something we sort of understand, and we see it manifested in nature in many different ways. But it's all kind of the same thing. Energy is the same thing. So the journey of the energy in this banana is truly amazing. Oops, I broke the banana. Dang it. Here, I'm kind of hungry, Phil. So what happened is millions of years ago, in the core of the sun, the pressure and temperature was so high that protons were able to crash into each other and overcome their repulsive force and fuse into helium nuclei. Nuclear fusion, stellar fusion. When that happened, some of the actual mass of the four protons that became a hydrogen a helium nucleus actually reduced a little bit. And by E equals mc squared, some of the mass became energy. Now that's at the core of the sun. The sun is huge. That energy made its way out as radiation through the sun until it finally reached the surface of the sun. And when it did, it was released into its environment as photons of light. Now, it took millions of years to get there. But then, I think it's millions of years. I might need to look that up. But then, it only took about 9 minutes to get to Earth. Okay, so, I don't know, a few months ago, some of those photons hit a banana tree, probably somewhere in Costa Rica or something. And that tree was able to capture that energy through photosynthesis and force molecules together in ways that they wouldn't do it if you didn't, push them together just right. And so those molecules became, sugar, carbohydrates, proteins, and fats. But this is mostly sugar. And this is a very delicious combination of molecules. Okay, now, the molecules in this banana, I want you to think of them as little tiny hand grenades, okay? They're little molecules they're like springs that have been squished and locked in place, okay? And then I eat them, okay? And so now I'm actually going to swallow, all right? And the banana material is moving into the stomach, and your stomach, my stomach's churning it all up, turning it into vomit, basically, and then if everything goes okay, it goes into my small intestine, where these molecules that contain energy are distributed through my blood system to all my muscles. And then those muscles are able to release the energy in those molecules and to do work and to make my hands move and to make my voice make sound and to keep my body temperature up, to keep my brain going, and to make changes to my environment. Okay? And so So basically, we're all operating, we all eat food, we're all operating on energy that was released turned from matter into pure energy in the core of the sun millions of years ago, and it's finally reaching you now, or reaching me right now. I'm going to finish this banana. Now, we all know what happens if you don't eat enough food. You get tired, you get hungry, and then if you really let it go on, you get kind of tired. And you stop moving so much. You're not making as many changes to your environment anymore. You're running out of energy. Eventually, too much energy. Eventually, you starve to death, okay, if you don't eat any food. And then you can't make any more changes on your environment at all. You're out of energy. Same thing happens in your car, right? You fill up your car with gas, and then your car will run out of if you run out of gas, you've run out of that chemical potential energy, and your car can't make changes to the environment anymore, can't move you around. So it's all about that energy. I want you to think about energy as the capacity to change the environment. Okay? Now, energy is stored up or exists in nature in various ways. And we're going to talk about many of those ways that energy is stored up during the course of this, the rest of the year. And one of them is through, well, okay, if I hold the bowling ball over your head, do you agree that if I release the bowling ball, right, changes will happen to the environment, right? You'll get a concussion, maybe a fractured skull. I'll very likely lose my job or my life from an irate parent. But in any case, that's called gravitational potential energy. Now, there's chemical potential energy, which was contained in this banana right here. And now it's being distributed into my muscles, right? And now that energy that was in the banana, it's in these bad boys right here, okay? Your muscles store energy. And then by applying a force through a displacement of distance, your body can transfer energy from its muscles into another system. So energy can be transferred from one object or system of objects, which we're going to call a system, into another system. So this thing we're going to call work, and I have to kind of start hurrying up here. Work is a transfer of energy from one system to another by using force. Okay, that's what work is. Work is, if you're doing what we call work, we're going to transfer energy from one system to another by using a force. Now, I'm kind of restricted to, this document camera here, but so you have to use your imagination a little bit. But if here's a flat surface, okay, and if here's like a crate on wheels, and it's just at rest. Now here's here's a small child playing on the street, okay? Yes. Now, this crate cannot affect any change to this child yet because it's not moving, and it's not. If I lifted it up with a crane and put it over the head of this child, yes, now I could say this crate could affect change on the child. We cut the cable and well, this is a terrible story. Okay, another way of doing it though is if I push on this crate, I could give it speed, right? I can give it velocity, right? If this crate was moving at 100 miles an hour, right? And here's a little small child, could this crate affect change on the child? Yes, it could. I found out I was hit by a car when I was, the summer before my junior year in high school. I was hit by a car, a very big car, and it had a lot of mass, and it was moving really fast, and it made changes to me, okay? And so therefore, because an object is moving and has mass, it has energy that it can transfer to other things. That's called kinetic energy, and we're going to study that a little bit later. So if somebody wants to give this thing energy, so here's some mean adult here, and they're going to push on this crate really hard. They're going to push on it, okay? And by pushing on it, what are they doing? So here's some applied force. They're going to transfer energy from their body into the crate. Now, in order to transfer energy from their bodies, right, they have to have chemical potential energy, and that's all, biology stuff that I don't understand. But they push on it, it moves through some displacement. Let's say you push on it through a displacement like this big. If it moves through that displacement, you've transferred energy into it. It now has kinetic energy, and it can make changes to the environment. And you did it by applying a force through it. Some people define energy as being the capacity to do work. If something has energy, it can do work. And work means applying a force through a displacement. I don't like to think of it that way. I think of work as just transferring energy from one system into another by applying a force to it. So let's come up with our definition now for what work is. Work is when I apply a force through a displacement. Work equals force times displacement. Now, by the way, this is the Science 1 definition of work. I mean, I taught Science 1 for many years, and we taught this stuff, and I said work is force times, we basically called it force times distance. We got to be a little more sophisticated in here. Well, what is this? This is newtons times meters, right? And we say a newton times a meter is a unit of work or a unit of energy that's been transferred, which means it's also a unit of energy. And a newton times a meter is called a joule. If you apply 1 newton of force through 1 meter of displacement, you have transferred 1 joule of energy. And we abbreviate it with a capital J. Now, let's suppose, using our imagination here with my picture, that this crate isn't here. Instead, there's a brick wall right here. Put a brick wall right there in your imagination. So this person is now pushing against a brick wall. Are they doing any work? No, they are not transferring any energy into the wall by applying a force. Why is that? Because you are not making the wall move. There is no displacement. Now, you are using up your body's energy, mainly by heating up the environment. Q, remember Q from chemistry? Q is heating, is a way of transferring energy into the environment by making molecules move faster. Okay? But they're not doing any work on the wall. Unless you're so strong that you can push through the wall and move the whole wall a certain displacement, which I have not yet been able to do. Okay? Now, let's take a look at another situation here. Here's a horizontal surface, and now I'm going to apply a force downwards like this. Okay? And it's going to be at a certain angle, downwards. Now, and here's this floor, and this floor is fixed and permanent, and you can't move, you can't punch a hole in it or anything, okay? Well, here's my force, but notice that the force now can be broken up into components. Here's the force, the horizontal component, here's the vertical component. I drew that too big. Fix that. So I think what you can see here is that this component of the force isn't doing any work, is it? All it's doing is pushing this crate into the ground, but it doesn't move into the ground. The crate doesn't. So you're not doing any work. You're not transferring any energy into the crate by pushing down on it, because the floor is going to oppose that force and isn't going to let any displacement happen. In other words, one way to look at it is that if you push down on this crate, if all you do is push down, here's an eraser, okay, this is my crate. If I push down on it, what's happening to the eraser? Nothing. Does the eraser, now that I push down on it, does it have the capacity to make changes to its environment? No. But if I push down on it and also with the horizontal component, I can make the eraser move. Now, a moving eraser has energy. It has kinetic energy, as we're going to describe later. So I did transfer some energy into it, okay, by doing work. So really what we want, what I'm saying here is that a force, only the component of the force that's in the same direction as the displacement is actually transferring energy into the object. That we're actually doing work. So if this is my angle between my force, I'll call theta is the angle between my force and the, the direction of my displacement, I'm going to say, oh, okay, well, this is, I want the horizontal component, that's cosine. So here's the regular physics definition of work. Work equals force times displacement times the cosine of the angle between the force and the displacement. Now here I'm using delta x because I'm moving it horizontally, but I don't have to use delta x. I can be moving this in three-dimensional space. So I can say, instead of delta x, I can say work is equal to the force times some displacement delta r. And you know what, let me take that vector hat off right now. Don't worry about it. Times the cosine of the angle between my force and my displacement. And that tells you how much energy you transferred into the object. Okay? And so this is really the regular physics, maybe getting into AP physics definition of work. And this is the equation that you're going to use to solve problems in this current section. Now, it is possible to do negative work. Let's talk about the difference between negative work and positive work. Let's take a look at a situation like this. I've got a crate. We physicists love crates. You know what I want for Christmas? I want a big crate. All right. And so here's my situation. I've got a rough surface. So here's my coefficient of kinetic friction. I'll just call this is m. And I'm going to apply a force to it. Like this. And this force is at an angle of theta. And here's my applied force. And because I'm running out of time, I'm just going to draw the free body diagram on the, including the plane. This is not very good thing to do, but oh well. So here's the weight of the object. I'm going to call that mg. Here's the normal force. Ooh, notice that I drew the normal force smaller than the weight. Why is that? Why would I draw the normal force smaller than the weight force? Because look at this applied force. It's got a component that's up. So it's actually lifting, it's actually supporting some of the weight, so the normal force doesn't have to support all the weight. In fact, the way I drew it, it looks like I might be lifting it off the ground. I'm not, though. I'm just kind of, but we've got a force of friction here, right? Now, let's say I drag this thing some delta x, like this. Okay, we're going to go drag it this far to the right. Now, let's take a look at how much work is being done by each force. Let's take a look at the normal force. Is the normal force transferring any energy in or out of the block? Well, work, remember that work equals the force times the displacement times the cosine of the angle between them. And so for the normal force, the work it does is, well, we got the normal force, whatever it is. We could figure it out by drawing a free body diagram, summing the forces in the y direction, and coming up with the normal force equation. But we don't need to here. Delta x is my delta r is actually delta x. What's the angle between my normal force and my displacement? It's the cosine of 90 degrees. And what is the cosine of 90 degrees? It's 0, so the normal force is not doing any work. Okay, because the equation tells me so. But think about it. It makes sense. The normal force is not transferring any energy in or out of this block. Okay, it's not making it move faster or slower. It's not lifting it up or lowering it down in a gravity field. It's not doing anything. Well, I mean, it's supporting some of the weight, but it's not, in terms of energy, it's not doing anything. Same thing is true with weight. Let's take a look at the weight. The work that the weight does is equal to mg times delta x, force. Now, what's the angle between the weight and the displacement? It's also 90 degrees. So in this case, this won't be true all the time. In this case, the force of gravity, weight, is not doing any work. It's not transferring energy in and out of this crate. Well, let's take a look at the applied force. How much work is it doing? Well, it's whatever that applied force is times the displacement times the cosine of theta. And it looks like, hey, theta looks like about 20 or 30 degrees, and that's fine. So and because this is, 30 degrees or whatever, this is going to be positive. What this means is that applied force is trying to transfer energy into the block. It's trying to make it go faster and faster, giving it kinetic energy, giving it the capacity to smash into things and cause and wreak havoc on the world, right? So it's adding energy to my system. My system is this crate. Well, what about friction? Okay, the work done by the friction force. Well, it's the friction force, whatever that is, mu times the normal force, and you could go through all that and figure it out, times the displacement, delta x. But what is the angle? You got to think, because I only got 2 minutes left. What is the angle between the displacement and the friction force?
180.
It's 180. Good. It's 180 degrees. Now, what is the cosine of 180 degrees? It's -1. So this is going to do negative work. Now, what does that mean? Negative work. Well, what is the friction force going to do? What is it trying to do? It's trying to slow it down. What if you got this thing going up to speed and then you let go of it? What's it going to do? It's going to slide to a stop, right? So something has to take its energy away. So if you have positive work means we're adding energy to our system. Now that energy in this class is mainly going to be kinetic energy or gravitational potential energy, which we really haven't defined yet. But when I add gravitational potential energy to an object, I'm lifting it up high. Okay? Or if I'm adding kinetic energy to an object, I'm making it go faster and faster and faster. Right? A bowling ball that's moving down really fast, but it's still high over your head, it's got a lot of energy, right? It can do a lot of bad work, all right, on your head. It can actually do. So negative work, when a force does negative work, it's taking energy out of the system. Am I off screen there? Yes. So positive work is adding energy to the system. In this case, my system is the crate. Or negative work is taking energy out of the system. This will allow you to solve all kinds of problems that would be very difficult using Newton's laws alone. But when you use the concepts of energy, a lot of very difficult problems become very simple. Anyway, that's it for today.